Hi guys, welcome back to Data Every Day. Today we're looking at some EEG data from hand movements. So basically we have 4 different users, user A through user D, and in each one we have a bunch of EEG readings while the user was performing various actions, hand movements. So I thought it'd be interesting to try to both predict the class of hand movement for a given user, and predict which user we're looking at based on the hand movement and the EEG readings. So we're going to have 2 different tasks today. One will be to predict the user based on the EEG data and the class, and the other will be to predict the class based on the EEG data and the user. So let's hop into the notebook. We're going to use a TensorFlow neural network to make our predictions. I'm importing NumPy and pandas for working with the data, and then we will be using the train test split function and standard scaler from sklearn for pre-processing, and then we'll make our models with TensorFlow. So let's go ahead and import those. And you notice we have 4 different data frames or CSV files, so I'm going to load them into a list to start. I'll call that dfs, which will be a list of all the CSV files converted into data frames. So we can turn them into data frames using pandas.readCSV. We put in the file path here, so I'll paste that in. And I want to do this one time for each of the CSV files. So this A, that's what changes in each name. I'm going to delete that, and I'm going to add in a user variable here. And that is going to be for every user in A, B, C, and D. So this will import user A's file, user B's file, user C's file, and user D's file, and store them all in a list of data frames. So now we have our DFs. If we index that at 0, we should get user A. If we index it at 1, we should get user B, and so on. So we have this list of data frames, and I'd like to pool them all together. For our task, for our purposes, we're going to take all these 4 data frames that we've just read from the CSV files and convert them into a single data frame that I'm going to call data. And we can do this using pandas.concat for concatenate dfs. So I'm concatenating this list of data frames along axis 0, which is the row axis. So this means stacking them on top of each other rather than side by side. And I believe that's all we need to do to see what data looks like. So here it is. Originally, if we look at just one of them, we have 2,880 rows. I'm not sure if they all have that number. They do, actually. So in the end, we end up with 11,520 rows, which is just 2,280 times 4, right? All right, so what are we going to do? I noticed that when we added all these together, we're no longer sure which data comes from which users. Obviously, we could figure that out just by looking at the indices, because this will reset 4 times from 0 to 2,879 and then repeat 4 times, but that's not a good way to know which user we're looking at, and the model won't know it that way. So what I'm going to do is, before we concatenate them together, I'm actually going to add an extra feature. So for I in range length of dfs, so it's essentially saying for each df indexed by I, we're going to take that data frame and we're going to create a new column called the user. And this we're going to, the user column will be a pandas series, and the value that the series is going to have is I. I here meaning the index of the user, right? Because we have 4 different users, and there's 4 data frames corresponding to each user. So if we index I, it's both indexing the data frame and the user. So I'm creating here, for example, if I take pandas.series of 0, well, that's just a single 0. And if we include index equals df sub 0 dot index, then it's a series of zeros of length 2880. So I'm going to do this for user A. For user B, we'll have a series of 1s. For user C, we'll have a series of 2s. And for user D, we'll have a series of 3s. And I'm going to create this new column for each of them that consists of that user's identification class. So let's include index equals df sub I dot index. And now we've added the columns, and if we concatenate them together, we have this new user column at the end, which takes values of 0 through 3, depending on what the original user, depending on which CSV file the data originally came from. Okay, so last thing I noticed is, well, currently our indices are all messed up. We have 11,520 rows, but you can see the indices go up from 0 to 2,879 and then reset 4 times. So I'd like to reset the indices, but I'd also like to shuffle the data because we have all the 0 users on top and all the 3 users on bottom, and so it's just it's completely ordered right now. So let's go and well, after we concatenate them together, we will sample 100% of the data. So sample, we specify a fraction of how much of the data do we want to sample. So we're sampling 100% of the data with replacement, without replacement, so that we're getting, it's essentially just a shuffle. That's all that is. And we'll also include a random state here so that we'll always perform the shuffle the same way when we run the notebook. After the shuffle's been done, the indices will also be shuffled, so we're going to reset the indices after, and that will also take care of the improper indices we have right now. I'm including drop equals true to prevent the old indices from becoming the new column in the data frame. Alright, and here we go. So now our indices are correct from 0 until this minus 1, and then the users take on values of 0 through 3, and they're all scrambled up. So this is a perfect way to deal with the data. And now you'll notice we have an additional feature in addition to all the EEG data, if we're considering the class as our predicted value. And now we can also use the user as its own class, as its target. So we will do both. Alright, let's create some helper functions. So what I like to do is one-hot encode whichever target column we aren't using, because these are categorical columns. Everything else in the data frame is numeric. I mean, we can take a look, take a peek just to see. Now we can't. Data.dtypes equals, actually we can do data.select dtypes object to see if there's any non-numeric columns, and does not look like it. And based on the description, I mean, I could go through every, you know, why don't we look at it? I'm going to do pandas.setOption max columns. I'm setting that to none, just so that we can now go through. You see, we can't see all the columns right now. So now that we set that, we can see all of them, all 114. And I'm just looking, I just want to make sure there's no categorical features in here, and there are not. I believe each one of these values, F8, F4, and so on, this corresponds to which electrode the reading is from. We also have different frequency ranges given by delta, theta, beta, alpha, etc. And we have the standard deviations and the means of each of those readings. So those are all continuous values, and the only categorical feature we would have would be either user or class, depending on which we are using. Which we aren't using as the target. So I'd like to actually set that back. I want to set the max columns back to 20 because I want to be able to see both the user and the class at the same time, like this. Okay, so let's get this done. Like I said, we're going to do one-hot encoding for whichever target we aren't using, since it's categorical. So let's make a one-hot encode function. Um, Note that I can one-hot encode using pandas.getDummies. So if I pass in here data sub user, so just the user column, this will be the dummies, where each of these is a different user. And we have a 1 depending on the original value for the example, and zeros for all the others. So here we have 0, 0, 2 in the first three. So here we have 1, 1, 1 in the 0 column, and then in the 2 column. So that's how one-hot encoding works. And we can also include a prefix here, call it user, so that we have names up there instead of just numbers. So let's create this function that's going to take a data frame, a column, and we'll start by creating a copy of our data frame. So this is the column we want to create dummies for. So let's actually create them and store them in dummies using pandas.getDummies for df subcolumn. And the prefix will just be the same as the column name in this case, because we're only going to be using class and user, and those are suitable prefixes. Alright, then we're going to take our data frame and concatenate together the original data frame and the new dummies columns side by side, so axis 1. And then we will drop the original column from which we created the dummies. Sorry, axis is 1. And then we will return df. So this one-hot encode should work. Let's test it out on data, and the column here will be user. So we've one-hot encoded the user column, and if we change this to class, we will one-hot encode the class column, and user will be kept like that. So like I said, we're going to use this on whichever target we are not predicting. Okay, now that we have that, let's go on to our pre-processing function. So I'll call this Preprocess Inputs. It's going to take in a data frame and the target that we want to predict. So by default, I'm making it class, but that could also be user. Alright, we'll start by creating a copy of our data frame and one-hot encoding whichever target column is not being used. So there's a few ways we could go about doing this. I want to reference the column that is not the specified target. So why don't we create a list called targets that will contain class and user. Then all we have to do is drop the actual target column. So targets.remove target, which is specified up here. Then the only thing remaining in the list will be the one that is not the target column. And so we can then call one-hot encode, our function, on data frame, and the column will be targets sub 0. To give you an idea of why that is, if we look at targets, and then we want to remove, so targets.remove, hold on, I just made this too small. Okay, targets.remove class. Then targets only has user, so if we index at 0, we get the user. Whereas if we remove user, we get class. So it's the inverse of whichever one we originally have. I mean, whichever one we specify as the target. So this will essentially one-hot encode the one that we're not using. And then we're going to split the df into x and y. So y here will be our target column, which is what we're trying to predict. So we can get that with df sub target. We'll make a copy of it. And x will be everything except the target column. So df.drop target. Axis 1. Alright. So if we return x and y, and just to look at what this looks like, x comma y equals preprocess inputs, passing in data, and the target will be the class. When we look at x, here's x. Our class is gone, and our users are one-hot encoded. Our class is stored in y now. And if we change this target to user, then our classes are one-hot encoded, and our users are stored in y. So it's sort of we'll change this value depending on which task we're trying to do. And then I also want to scale the data. So currently these all take on different ranges of values. I believe they refer to frequency ranges. But you can see we have some small values of 1.0, 1.4, 0.8, and over here is in the thousands. So I'd like to sort of standardize them so that all the columns take on the same range of values. And we can do that using a standard scaler. So I'm going to scale x with a standard scaler. A standard scaler will give each column a mean of 0 and a variance of 1. And before I actually do it, I want to do my train test split. So this is going to separate our, we're going to take some percentage of the data and store it in the train set, and the rest will go to the test set. And we can use that using train test split function from sklearn, which I imported earlier. We're going to split x and y at the same point, and we'll specify a train size. We'll use 70%, and we'll include a random state. This is because this function actually also shuffles the data by default. So by including the random state, we can ensure that the shuffle and therefore the split will always be made the same way when we run the notebook. And this will return 4 new values: xtrain, xtest, ytrain, and ytest. Alright, and now we can scale. So I'm going to create a new scalar object, standard scalar. That's also from sklearn. And then we're going to fit the scalar to the train set. Note I'm not scaling y. This is why I split them apart, because y needs to be kept as the class label, so we don't want to mess around with the values. But in x, each column can be scaled because that's going to be our input. And don't worry, we can also scale the one-hot columns. That's not a problem, because it's taking into account the relative differences between the values in the column. So it won't really recognize a difference between a 1 and a 0 and some other value, because the one will be higher than the other. Alright, so we're fitting it to the xtrain, and we're going to transform xtrain and xtest using the fit that we have on xtrain. So scalar.transform, and here we're transforming xtrain, and here we're transforming xtest. Now I would like to point out that this function returns a NumPy array, and I'd like to keep it as a data frame with all the column names intact. So I'm going to turn it back into a data frame after we've transformed it. And the column names will be x.columns. Alright, so I'll just copy that over, copy this over, and we should be good to go. Last thing I want to do is, well, actually I just want to return xtrain, xtest, ytrain, and ytest. Okay, let's get those values over here. And now if we look at xtrain, it's only 70% of the data now, but it's the same format as before. And you'll notice that all the columns are scaled, so that the means of each column are very close to 0, and the variances of each column are very close to 1. So they all take on the same range of values. Alright, and then ytrain just looks like this. This is all of our user data. If we change the target to class, then ytrain will be all of our class data, and the user columns show up here. Alright, then our last helper function. So I'm actually going to save that for later. That will be in predicting hand movement class. So if we're now predicting, we're going to do the class first, predicting the class. So we're keeping target as class, and then we get our data here. Let's look at some of the unique, let's actually look at the counts of each value in ytrain with value counts. And you can see class 0 has, they all have about the same number, so pretty even class distribution. And now we need to build our model. So make a new helper function, and I'm doing it as a function here because we're going to call it twice, build model, and we're going to specify a number of classes. By default, it will be 3 because there are 3 class target values. Alright, let's start by creating, no, we don't have to create a copy, sorry. Let's start by defining our model architecture. I'm just going to use a standard Keras two hidden layer neural network. The input will be tf.keras.input with a shape given by, it will be a tuple vector of length xtrain.shape sub1. Because if we look at xtrain, if we look at the shape of it, you can see it is 8,063 rows by 116 features. And if we check just sub1 of that, that's the number of features. So on a given example, we have 116 values coming in. So here, that's what this value is. Then we're going to create 2 layers. They'll both be dense layers with 128 activations and a ReLU activation function. The first one I'm going to pass in inputs, and the second one I'm going to pass in x. So it's just feeding through. And then our outputs will be also a dense layer with num classes activations. This is how many output classes we have. We're specifying it up here. And the activation function here will always be softmax, since both tasks we're doing are multi-class problems. And then I'm passing in x, and then we'll create the model here. Model equals tf.keras.model. The inputs will be defined by inputs, and the outputs will be defined by outputs. Alright, and then we'll compile the model. So we're going to use an atom optimizer for both. And our loss function will be sparse categorical cross entropy for multi-class loss. And then our metrics, we're just going to use accuracy. Alright, so after that, we will return model. So this is going to build the model, it's going to compile it, and then it's going to return the compiled model. Alright, and that's all we have for helper functions. Now let's get into actually predicting. So let's create the new model. We'll call it class model. And class model will call our build model function, and we'll specify the number of classes to be 3. Then we're going to fit the model, class model.fit, on xtrain, ytrain, and we'll give it a validation split 20%, a batch size of 32, and we'll train for 50 epochs, but we'll also include a callback function, which will be tf.keras.callbacks.early stopping. So this will look at the validation loss, or whatever value we pass into monitor here. So val loss is what we'll look at, and it'll note, it'll see if val loss is improving, and if it stops improving for a given number of epochs given by patients, let's say 3 epochs, then we'll stop the training, and we will restore the weights from the best model. So restore best weights equals true. And then I'm going to store the results from this fit in class history. Alright, so it's training. It shouldn't be too long. It should early stop as soon as it notes that the validation loss stopped increasing. And it looks like we had our best epoch around here with a validation accuracy of about 61%. So now if we can get the test accuracy to see how it does in unseen data. We'll call it class accuracy, class ac. And we can get that with class model.evaluate, and we pass in xtest and ytest. I'm going to turn off verbose mode, and then I'm just going to get the second value it returns, because this will return the loss and the accuracy from the test set. So I just want the accuracy, so I'm doing sub1. And then we'll print out test accuracy on the class model, and we'll display it to 2 decimal places, the % sign after, and format with class act times 100, so I want it as a percentage. Alright, and 61.8%. So there's a bit of randomness to this. If we run this again, we could get a slightly higher or lower. I noticed sometimes we get up to 64. Unfortunately, it's very difficult to get TensorFlow to behave in a deterministic state, even if you set the seeds. It's really not a big deal. We're getting a range of about 59 to 64% accuracy on this. So looking at other notebooks on Kaggle, it seems about right. Some people I noticed used a recurrent neural network for this, which I could see as working as well. I just picked this sort of standard model because these are sort of standalone features, and RNNs tend to take a lot longer to train. Then let's move on to predicting the user. So this is very similar to what we did before. Only difference is here. So I'm going to overwrite xtrain, xtest, ytrain, ytest. We could call them different things if we wanted, but I'm not going to. The target here is going to be changed to user. And if we look at that now, like we saw before, we have our classes now as features and our users as the classes. So let's take a look at what kind of values we have in here with value counts. And it's a pretty even class distribution. To build this model, all we have to do is grab the code from up here, because it's very similar. Only difference here is the number of classes is 4 now. And we can just rename these, instead of class model, class history, and here we'll change it to user. So we have user model and user history. Alright, and it looks like we're doing much better on this one. It seems much easier for the machine learning to predict the user based on the data than it is to predict the hand movement. So let's actually take a look at the test accuracy. This time, instead of class, it's going to be user. And here. And this will be the user model. Alright, and it's quite high. Very, very high. It seems almost easy for the model to figure out the user, which sort of makes sense, I guess. Alright, and I guess that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.